In this lesson, we'll cover wavefronts and rays and the topics of superposition and reflection. This is a simulation from PhET, and here we see water dripping into a pool, and the bright and dark regions are representing crests and troughs, respectively. If we take a look at this graph, we can see that every bright region is a crest of a wave, and every dark region is a trough. And so a single wavelength is from one bright region to one bright region, a crest to a crest, or a dark region to a dark region, a trough to a trough. And now here from the same simulation, we see these planar waves that are moving out towards the right. They're flat waves, and we can consider each of these crests or troughs as a wave front. So if I stop this, each of these is a wave front, and we could draw them like that, like straight lines, although I'm having trouble drawing straight lines like this. Now, that's one way of modeling the waves. Another way is to draw a line that goes from the source outwards that is perpendicular to all of the wave fronts, something like this. And this we would call a ray. So the ray is perpendicular to all of the wave fronts. So again, one way of modeling waves is to draw them as wave fronts like this that are connections of all of the crests to all of the crests, or all of the troughs to all of the troughs. Those are wave fronts. And I could also draw a ray that is perpendicular to all of them, moving off towards the right. This is the ray, and in blue we had the wave fronts. Again, they're perpendicular to each other. And the same thing is going to happen if we are going out in all dimensions from a central source. So we would have circular wave fronts around it, and then the rays would be perpendicular to those circular wavefronts coming out like that. So two different ways of thinking about waves and drawing them that are going to be useful in different circumstances. Now let's talk about the principle of superposition. The principle of superposition says that when you have two or more waves that end up overlapping at the same place at the same time, and we call this overlap interference. When we have two waves that are in the same place at the same time, then we get a resultant wave, the amplitude of which, or the displacement of which from the equilibrium, is just the algebraic sum of the individual displacements of the two waves. Algebraic meaning we care about the sign. So let's take a look at what that means. This simulation is from O Physics, and what you're going to see when I press run is that this wave and this wave move towards the center of this string. And as they overlap, the overall displacement of the string in the dark black line is equal to the sum of the individual displacements from the two different waves. And it's going to help you keep track of the displacements that result from each individual wave by showing you this orange and the blue line. The blue line actually corresponds to this wave. It's flat because this wave is all the way over here, and so it's not displacing the string over here, and vice versa for the orange. So I'm going to slow this down actually quite a bit and press run. And then you'll see after they go through each other, they get back to just the original shape that they were. So they emerge out the other side completely unchanged, and that's another aspect of this superposition. Once they get to the end, they're just going to bounce back, and you'll be able to watch it do the same thing several times. So here they go. I'm going to speed it up actually just a bit. You see them pass through each other, and then they emerge out the other side unchanged. We'll watch them do that again, and notice that you can follow the orange and blue lines to see the shape of the original waves, as well as the overall shape of the sum of the two of them. I'll speed it up now a little bit now that you're getting used to it, and you can see that the overall sum is greater than either of the two of them, and we call that constructive interference, when the overall displacement is greater than the displacement that resulted from either of the individual waves on their own. Now I can turn this around and make one of them upside down, and now watch what happens. We see that there are points when the sum of the two of them results in a displacement that's lower than the amplitude of either wave. And so the displacement is less than it would be because, again, it's an algebraic sum. It's a positive from this wave and a negative displacement from this wave. I'll slow that down so you can watch that a bit more. And so there you see in the center, we've got some times when we even have zero displacement at certain parts. And if I made the waves completely symmetrical, now they're completely symmetrical but upside down from each other, then we'll see that there's actually going to be a point in the middle where we got actually a completely flat wave. Let's see if we can catch that again. Okay, I'm going to slow this right down. and we'll see that there's a point in the middle where the sum of the two of them is actually just no displacement whatsoever. Now this is called destructive interference, where the sum of the two waves is lower than the displacement from either one. And here it comes here. We have a flat line, and then they pass through each other unchanged. So that's constructive and destructive interference. So to summarize, in constructive interference you have two waves or two pulses that come together and result in a displacement that is greater than that from either wave individually, and then afterwards they are going to continue on their way unchanged from before, so they pass through each other. In contrast, destructive interference is when you have a displacement that is less than that of either individual wave. So I've tried to draw these symmetrically but didn't do it very well, and we saw that you could have a completely flat line and then afterwards they're going to pass through each other like that. And we're going to see that this interference becomes important in all sorts of different wave phenomena. Now we saw waves reflecting back and forth in the previous simulation, so let's just talk a little bit about how waves reflect. Now this is back in the FET simulation, and we've got a string with no end, and I'm going to send a pulse through it, and no surprise, it just disappears and we don't see it again. Now I'm going to change that, and I'm going to make that a fixed end. We actually have two fixed ends now. We have this one, and this will become a fixed end after the pulse is gone, because the motor is not going to be going sending this rod up and down anymore. So we have two fixed ends, and I've taken all the friction out of the system, damping is set to 0. Let's watch what happens. I send a pulse down, and as it gets to each fixed end, notice that it reflects upside down from its previous orientation. Here it's right side up, now it's upside down, if we think about which way the peak is pointing. So at each fixed end, the one on the right and the one on the left, it's flipping upside down. Now if I were to change that and to make that a loose end, here you're going to see that this ring can just slide up and down the pole, so it's not fixed. We'll see something different. Now, at the loose end, it returns right way up, but over here, because this is still a fixed end, it flips. So it's flipping here, but not here. So that's a difference between what's happening at a fixed and a loose end. Now let's think about why that's the case. On the left, we see a pulse moving towards a fixed end. This is a wall, and here we're going to see the after. This is the before, this is going to be the after. So it's moving in this direction, and I've drawn it so that it is asymmetric so that we can also see another feature. We have seen that it flips upside down, and the front is going to stay in the front, meaning that if this part is leading, here it's going to be leading again. So that's what this one's going to look like, and we've seen that in this case it's going to look like that. Okay, so it turns around, the pointy end here ends up here in both cases. So think about this point in both situations. Here we have a fixed end, and if you imagine the string pulling up on the wall, then by Newton's third law, the wall is going to pull down on the string, and that's essentially what's flipping this upside down. It's the downwards pull of the wall on the string that is leading to the flipping upside down, whereas in this case there's no such force. And in fact, if you go back and watch the simulation, you'll see that there's an overshoot where the ring ends up way up here, and that's because at this point, in contrast to every earlier point, there's no piece of string on the next side holding it down. Every piece of string along the way here has been pulled up as this has moved to the right. This piece of string, for example, is getting pulled up, but it's also getting pulled down by its neighbor to the right. That's not the case here, and so this one ends up shooting up more than any of the other bits of string before it did, and that phenomenon is why it stays upright. So fixed ends are going to flip pulses upside down, and free ends are going to keep them right side up.